Hello everyone! Having discussed the behavior of a single local magnetic moment in an external magnetic field, we now turn to a macroscopic system of local magnetic moments in a solid. Our purpose is to calculate the experimentally measured magnetization as a function of magnetic field and temperature. Let us consider that atoms of solid are fixed, and all of them have magnetic moments. Let us also consider that these moments have the same absolute value, but various direction. Recall that according to quantum mechanics, the projection of each magnetic moment on certain z-axis can adopt different values, not any, but only discrete values. For the sake of simplicity, let us consider that the spins of all atoms are the same, and all of them are equal to 1/2. In this case, the z component of the atomic magnetic moment may take only two possible values. Two types of interactions contribute to the total energy E of such a system. The first is the interaction of each magnetic moment with the magnetic field, and the second is the interaction of the magnetic moments to one another. The expression for the total energy has the following form. Thus, the Hamiltonian looks like this. Taking the z-axis along the magnetic field, we finally obtain for the Hamiltonian the following expression. In the case that magnetic moments weakly interact with one another, for example because of their low concentration or small absolute values, one can neglect the second term u in the Hamiltonian. Then the Hamiltonian of the whole system is just the sum of Hamiltonians of individual magnetic moments, each being in the magnetic field. And for the thermodynamic average of an arbitrary kth magnetic moment, we have the following expression, where trace k and trace I stand for the trace over the states of respectively kth and all other magnetic moments. For the details of calculation the temperature dependence of any physical quantity, look for the appendix, which is called Interplay of Quantum Mechanics and Statistics, at the end of this lesson. Remember that we consider the case that every magnetic moment in the system be associated with spin which is equal to 1/2. Then the value of mu kz of t for an isolated magnetic moment has the following form, we already know this, while the projections on x and y axis are equal to 0. Since all magnetic moments are identical, the total magnetic moment of the system consisting for capital N magnetic moments is n mu k of t, so we can obtain the magnetization. In weak magnetic fields, we have from the previous equation for magnetization the following approximate equality. Note that the ratio of T and mu0 is about 1 Tesla at temperature is equal to 1 Kelvin. So, magnetization M is linear in magnetic field H, and the magnetic susceptibility takes the following form. Such temperature dependence of chi is referred to as Curie law. Curie law looks like this. The fact that chi is greater than 0 implies that materials containing non-interacting or weakly interacting magnetic moments are paramagnetic. The magnetic moments of such material are oriented along the magnetic field, so the magnetic field inside the material is become stronger. Measuring the chi, the proportionality factor can be obtained. Knowing this factor, we can obtain either the concentration of magnetic moments, if we know the mu0, or mu0, if we know the concentration. As a result, if the atoms of a solid have local magnetic moments, and they are weakly interact with one another, then this solid is a paramagnet. We see that at 0 magnetic field, the magnetization is 0 as well, at any temperature. This is true for many materials, but not for all. There are materials with local magnetic moments with non-zero magnetization at 0 field at high temperatures. How to explain this? Recall that we neglected the intermoment interaction. However, we cannot do such approximation in ferromagnets. Let us try to take it into account. At 0 magnetic field, the magnetization of a system of non-interacting local magnetic moments is zero at any temperature. Meanwhile, there exist materials, ferromagnets, for which magnetization is non-zero at zero field provided the temperature is below some characteristic value, theta, called the Curie temperature. It seems reasonable to assume that the failure of explanation the occurrence of such materials within the model of non-interacting moments is a consequence of ignoring the interaction of magnetic moments with each other. Weiss was the first who appreciated this. On this slide, the first page of his original publication is shown. Weiss introduced his theory in 1907. Weiss noted that once the magnetic field is applied to the sample, each moment interacts not only with this field, but with the field created by all other moments as well. Since, first, the magnetic field induced in the sample by an external field has the following form, and second, the field generated by the ith magnetic moment has no effect on this moment itself. There is no self-action. So the net field acting on ith moment has the following expression. Taking into account that the value of averaged mu k does not depend on k, we have the final form for net field. The second term is called the molecular field, or the Weiss field, and the net field is named the mean field or the effective field. Each magnetic moment experiences the effective field, so that the Hamiltonian has the following form. Making several calculations, we can obtain the Hamiltonian of a system of non-interacting magnetic moments in an effective magnetic field. By analogy with the isolated local magnetic moment in an external magnetic field, we have the following equation. Let us examine whether this equation has non-zero solutions at zero field. Taking into account that hyperbolic tangent is a monotonical increasing function of z, being linear in z at z is much lower than unity, and approaching plus minus 1 when z tends to plus minus infinity, we conclude that our equation has just one trivial solution, x is equal to 0, at t is lower than theta. While at t is greater than theta, there are three solutions, one zero solution and two non-zero solutions. It can be shown that non-zero solutions correspond to the lower free energy of the system. That is, they are thermodynamically more stable. So, at t is lower than theta, the average values of all magnetic moments and hence the magnetization are non-zero even in the absence of the external field. This is just what is referred to as ferromagnetism. Let us estimate the value of the Curie temperature theta. Taking for lambda, concentration and mu 0 the following values, we have the upper bound for theta is equal to 1 Kelvin. Meanwhile, ferromagnetic materials, this theta is about 1000 Kelvin, do exist. To explain such high Curie temperatures within the Weiss approach, one should assume unrealistically large values of lambda, concentration and mu 0. Hence, the Weiss idea appears to be at variance with experimental data. Moreover, numerous experiments revealed that the molecular field generated by the local moments is, if any, orders of magnitude weaker than that required to account for the phenomenon of ferromagnetism. Surprisingly, based on the mistaken assumption, Weiss arrived at qualitatively, although not quantitatively, correct results. The main merit of Weiss is that he has pointed to the necessity of account for interactions between the local magnetic moments. What are the main conclusions of this lesson? There are two types of interaction contribute to the total energy of the system of magnetic moments in an external magnetic field. The interaction of each magnetic moment with the magnetic field and the interaction of the magnetic moments to one another. If the atoms of a solid have local magnetic moments and they are weakly interact with one another, then this solid is a paramagnet. So, at zero magnetic field, the magnetization of a system of non-interacting local magnetic moments is zero at any temperature. The temperature dependence of magnetic susceptibility in paramagnet is defined by the Curie law. In a paramagnetic material, the magnetic susceptibility of the material is inversely proportional to temperature. Thus, it is necessary to take into account the interactions between magnetic moments in a solid. Weiss was the first who understood the necessity of account for interactions between the local magnetic moments. But his theory cannot explain the high Curie temperatures of ferromagnets. Below we shall see how such interactions naturally arise when the problem is treated quantum mechanically.